Now, let's see how to implement the second-order optimization in Julia. First, let's review what is the Jacobian matrix and Heisen matrix. There are actually two versions of Newton's method. Today, we are going to talk about finding the roots of a polynomial, all these points where it intersects the x-axis. We define a function named Newton method of initial, f, and limit time. Initial refers to the guessed point we give initially, and in this function, we initialize the step size as 1, but it can be different. After having computed the equation, we can get a new point, comparing the value of function with these 2 points to check if the step is accepted. If the new value is smaller than the old one, then it will be accepted and the step size will be changed into bigger or remain the same. Here is an example for the Newton method function. We define a function randomly and set the initial point to be 1, 2, 3. Using Newton method function, we find the value of x that minimizes the function. The Gaussian-Newton method can only be used to minimize a sum of squared function values, but it has the advantage that the second derivatives are not required. We define the function named Gaussian-Newton of initial f, data, limit time, and limit distance. In this function, we have defined what the residual function is, but it can be different. Fs means the data generated by the residual function with the value of x. Js is the partial derivative of function with respect to the parameters, and evaluate the partial derivatives at the data to get matrix using the initial values of A. Stop if the method has met any of the desired convergence criteria or has excluded the limit of function evaluation or iterations. Here is an example. First, we define a function to help us generate data. Then we define a function A to help us fit the data generated by function B, and assume all the parameters of function A is unknown. Then we apply the Gauss-Newton function we defined with the initial point 1, 2, 3, 4. Then we can get the value of parameters of function A with that. After that, we can get the residual of using this method is nearly 51. The Levenberg-Marquardt method acts more like a gradient descent method when the parameters are far from their optimal value, and acts more like the Gauss-Newton method when the parameters are close to their optimal value. The front part code is the same as Gauss-Newton method, but the differences are when we try to estimate the new values of parameters, we need to consider lambda, the damping. Accept or reject the parameter step depending on whether the cost has decreased at the new parameter. In order to compare Gauss-Newton method and the Levenberg-Marquardt method, we use a complex function as example. First two-step is to generate data by using function we defined and build a nonlinear function to fit this data. First, if we use Gauss-Newton method, we cannot get the value of 4 parameters. But if we use Levenberg-Marquardt method, we can get the value of 4 parameters and the value of residual.